Welcome, everyone, to today's Explainer. You know, we use computers literally every single day, mostly just treating them like magic black boxes. But today, we're going on a fantastic voyage. We're going to completely crack open that box and take a deep look into the physical and logical brain of a computer system. We're breaking down the sheer anatomy of these machines to see exactly how all their structural components actually come together. Okay, let's dive into this roadmap. First up, we'll look inside the machine blueprint. Then, the limits of performance. Next, we're navigating the memory hierarchy, followed by cracking cache memory codes, and finally, architecture versus organization. All right, Section 1, inside the machine blueprint. This is where we lay down the foundational skeleton of computing-based systems. Before we can even think about optimizing any machine, we have to really understand how to arrange its basic parts. Consider this our first major skill unlocked. We're not just staring at a jumble of wires here. We're applying real engineering fundamentals of computer organization, and doing that helps us make absolute sense of computing-based systems. So any basic organization of a computer relies on block-level functional units. You can kind of think of these as the distinct organs of the machine. Traditionally, we rely on the von Neumann model as our baseline. It's a brilliant setup that unifies how a computer processes instructions and data, right there within the same shared memory space. But on the flip side, for a little self-learning, check out the Harvard architecture. It's an alternative that actually splits them into separate, parallel paths. Getting a grip on these foundational units really sets the stage for everything we're about to cover. Which brings us to Section 2, the limits of performance. And spoiler alert, things are about to get a little tense because we are running straight into the literal laws of physics here. Because as much as we'd love to, you can't just make a computer infinitely fast. Eventually, you are going to hit a bottleneck. And that brings us to Amdahl's law. Basically, it's a formula used to find the maximum improvement possible when you're improving just one particular part of a system. It's kind of like dropping a screaming fast Ferrari engine into a giant heavy tractor. I mean, sure, the engine is great, but your top speed is still going to be severely limited by that massive, clunky chassis. In the math behind Amdahl's law, the number 1 represents a hard, theoretical limit. It represents the entire task, 100%. And it acts as the absolute ceiling on the speed-up you can possibly achieve through parallel processing. Look, no matter how much processing power you throw at one specific chunk of your system, the unupgraded parts, they'll always act like an anchor on your overall performance. So because these basic measures of computer performance dictate the absolute speed limits of our system, engineers know they can't just rely on brute force. They have to get incredibly clever. They have to design brilliant workarounds to cheat these physical bottlenecks. And that leads us perfectly into Section 3, navigating the memory hierarchy. This is where we solve some of those major bottlenecks by getting really smart about where data actually lives. We have to balance a pretty massive spectrum of storage, right? At the very bottom of this landscape, we have slow, deep, high-capacity storage, things like optical memory and RAID, which stands for Redundant Array of Independent Disks. Moving up the speed ladder, we hit flash memory. And finally, sitting right next to the processor, we have lightning-fast active storage, like DDR DRAM or Dynamic Random Access Memory. The ultimate goal here? To give the computer the illusion of an endless, instantaneous memory pool. Okay, Section 4. Cracking cache memory codes. Get ready, because this is the ultimate hack to beat those bottlenecks we just talked about. So even that blazing fast RAM isn't quite fast enough sometimes. Enter cache memory. This is ultra-high-speed storage specifically designed to solve performance issues using a very cool concept called locality of reference. Think of it like a workspace. If your hard drive or RAID array is a big filing cabinet down in the basement, and your main memory is the physical desk you're sitting at, cache memory is the sticky note slapped right onto your monitor. It holds the absolute most urgent data you need this exact millisecond. But how does the computer actually know what to put on that sticky note? Well, it follows a super simple step-by-step procedure based on that locality of reference. Step 1, the CPU checks the high-speed cache. Step 2, if there's a mess, meaning, hey, the data just isn't there, it runs all the way down to the slower main memory disk to find it. And Step 3, it fetches that data and, crucially, copies it to the cache for next time. The logic is brilliantly simple. If you used a piece of data recently, you're probably going to need it again very, very soon. As you can imagine, though, organizing thousands of those sticky notes is a massive logistical challenge. This is a crucial engineering skill. We have to use highly appropriate mapping techniques to allocate data. We need to figure out exactly how to grab a massive library of information from main memory and map it perfectly into the tiny, precious real estate of those cache blocks. Now, what's really interesting about this slide is how we break down these complex design problems. For mapping techniques, we use strategies like interleaved and associative memory to determine exactly where the data belongs. For integrity, we maintain something called cache coherence, which basically ensures that if data changes in the cache, the rest of the system immediately knows about it. And for data management, we rely on strict writing policies to dictate exactly when and how that updated information gets written back down to main memory. And here's why this matters. When you fully master mapping techniques, cache coherence, and writing policies, you are no longer just observing the machine. You're actually designing a custom cache memory system based on specific requirements and data to completely bypass those physical computing bottlenecks. It's a total game changer. Finally, Section 5, Architecture versus Organization. We're bringing our journey full circle here to look at the macro picture once again. And this brilliantly illustrates the difference between the core idea and the physical reality. Computer architecture is the logical design. We're talking about the instruction sets, the core concepts, what the computer is theoretically capable of doing. Computer organization, on the other hand, is how that hardware is physically implemented. It is literally the difference between an architect's beautiful blueprint for a house and the actual bricks and mortar the builder uses to construct it. So we've seen the blueprints, we've explored the memory hierarchy, and we have pushed right up against the absolute limits of performance. But honestly, it leaves us with a massive looming question. With Amdahl's law permanently capping our speed, and physical cache memory getting as small as atomic physics will even allow, what does the next leap in computer engineering actually look like? When we can't shrink the sticky note any further, how do we rebuild the desk? Thank you so much for joining me on this explainer. I really hope it sparked your curiosity to look deeper into the systems powering our world.